Hello.
Good afternoon, sir.
Yeah, good afternoon.
Good afternoon, sir.
Yeah, good afternoon. So, yeah, so before I start, as usual, you have any questions, doubts on anything that has been solved, done in the class in the last class or last few classes? Also, of course, I returned your papers, so I guess you guys have seen it. So if you have any problems in or some doubts in that respect, you can just let me know. Okay, so no doubts. Just 1 second. কেন? হ্যাঁ আমি পরে করছি তো। Hello. Yeah.
Yes, sir.
Yeah. So so today we will be going a little bit slightly different from what we have been doing. Not exactly. So just one thing. Just before I start, just let me ask you one thing. In your okay, I think I need a couple of minutes because my this pen in iPad pen is out of charge, so I have to take some time. So anyway, so in your discrete math course, did you do things like network flows?
Yes, sir. We did a theorem.
Yes, sir, we did.
You did a
Ford Fulkerson, I think.
Yeah, you did Ford Fulkerson?
Yes, sir.
Okay, good. So maybe before so you know what a flow is, right? Network flow, right? So I have a graph and I have a start state and a
Sir,
end
are you
state.
sharing your screen?
No, I'm not.
Okay.
I'm not because as I told you, my pen is run out of charge, so give me 2 minutes while it charges.
Okay.
Yeah.
Sir?
Yeah.
Sir, I had a question from one of the earlier.
Oh, sure. Yeah, go ahead.
Sir, in one of the classes, we had discussed that any minimum spanning tree could have a cut property, or we can find a minimum spanning tree which has a cut property.
What do you mean by cut property?
That if we take any partition of the vertex set,
right,
then it may include the lowest weighted edge.
Correct. Yes.
Across.
Yes.
So this was a forward implication that we had discussed, but is the reverse true?
No,
that...
I mean reverse is true in the sense that if you have a unique minimum edge, okay, in a cut, if you have a unique minimum edge, then that edge has to be there. Okay.
But we are saying that if a spanning tree has the cut property, then can we say that it should be like, so if a spanning tree has the cut property for any partition, can we claim that it is a minimum spanning tree?
So if you have a spanning tree has this cut property, good question. I think
so long as sir, is it necessary? I think the set of vertices has to be part of some MST for that.
No, he's saying that look at all of the spanning trees.
Okay, all of them. Okay, maybe I'm not understanding the question.
Among all the spanning trees, if I give you a spanning tree, and in that case, the cut property is satisfied, meaning in any cut, the minimum edge, take any cut, the minimum weighted edge, or at least one minimum weighted edge, is there in the spanning tree.
Okay.
Then is it
actually, sir, where I'm coming from is, if you think about the graph of trees, this is a concept that was introduced in one of the quizzes, I think.
Right.
Where we denote every single vertex of a graph as
Yeah.
a spanning tree, and then we can hop across
Right.
this graph where two trees are adjacent if they differ by one edge only.
Hmm.
So the question is motivated by the fact that we know that if we can do this edge removal and introduction such
Hmm.
that the sum of the the sum of the edges in the tree decreases, then we can head towards a local minimum, let's say. But then whatever local minimum we head to, if we
Yes.
want to claim that it has to be the global minimum, then
Yes.
we need
You
this
need something.
characteristic
Yeah,
property.
I think this is statement is true actually. What you just now told, this kind of this fact about the, if I have a tree which satisfies this property, the cut property that you are saying, right? That I think it will be a MST.
Okay.
Yeah, you can try to prove this one. It's kind of similar proof actually. I mean, we
Right.
will- yeah.
Because I felt that in this last assignment,
Hmm.
at least in one of the proofs, we needed something like this to claim that it is an MST.
Hmm.
Like the one of the questions was that if we were to look at a graph which already has a given spanning tree, a
Hmm.
given MST, sorry, and then we were to change the values of one of the edges,
Hmm.
and we now had to find the modified MST.
Right.
Now we can propose an algorithm which is greedy in the sense where we just replace one of the edges and basically look at a tree which is adjacent in the graph of trees.
Hmm.
But then to prove that that is the MST, I think we would need something like this, right?
Right.
I'm
Right.
not.
Yeah, you're
So-
right. You're right. This is, you have to get that one. I mean, and the proof is not hard actually. Proof is basically the very graph theoretic, so you can try to prove it.
Okay.
Okay. Any other questions? Any other comments or something? Okay, so let me start something with a very simple thing. That's what I was saying to you guys. That
You
yeah.
Sir?
Sorry.
you also left a problem in the
Yes,
last tutorial.
In last
So
tutorial.
the
what-
online the prison break problem.
Yeah, present break problem. Okay. Okay, let's come back to that last. Okay, I don't want to really derail this whole class because of that.
Okay, sir.
Okay,
Okay,
so
sir.
just remind me at the end. I will talk about it.
Okay, sir.
Yeah. So good. So I want. So we are talking about network flows. You can see my screen, right?
Yes, sir.
Yes, sir.
Yeah. So what is the network flow? So you have a graph G, and you have a vertex, starting vertex and a ending vertex, right? And we have, of course, the weights associated to each of the edges. Just for now, assume it's positive weights, and I want to find a flow, right? What is a flow? A flow is basically, again, for every edge weights, for every edge, I have to give you a real number. Okay, so by the way, this is a directed. Okay, so I should write it that this is a directed graph. So every edge there is a positive number, such that what? Let me see whether you guys remember. So it's kind of saying that if I think of this edge weights as, or edges as pipes, kind of stuff like that.
Sir, there are 3 conditions. Actually, 2 conditions.
There are 2 conditions. You are completely right. Okay, so but let me just quickly tell it. So say I have things like this, some graph like this. Okay, and I have edge weights, say 1, 3, 9, 2, 10, 4, 5, 4, 8, 3, 1, 2, 5, 6, and so on and so forth, right? Now it's like if you think of this edge weights as kind of telling this is the width of a, so as the edges as pipes and the wedge weights as the diameter of the pipe, right? So it's like the amount of water that it can pass through at any moment, right? And you're kind of, you have an infinite supply from here, S. The question is that how much supply can you take out from T? And that is basically why the flow concept comes in. So you have a restrictions, of course, like I can send a lot of mass. So for example, so maybe I should just change a little bit here. So I can say that this is say 7. So if I send 10 units through this direction, then I can of course send 7 units here, 2 units there, but that's not good enough because I cannot have water stored in, right? So there are pipes. The pipes will burst. So of course you cannot send 10 units through this and send 7 and 2 because from this point 7 plus 2, 9 units are going out, but 10 units are coming in. So good. So that cannot be done. So that means I should send less than 10 units through this flow, right? And we want to maximize the flow. So as somebody pointed out, can you guys tell me what are the flow conditions that are there? Yeah, who was it who was telling it? Hello. Nobody. Hello, am I connected?
Yes, sir.
Yes, sir.
Yeah. So what are the flow conditions?
So 0 lesser equal to Fe lesser equal to We for all edge.
Excellent. So the amount of flow that goes through a edge must be less than the weight of the flow. That's like the condition. So this is for all E. And what is the rest other one?
So from source to T, the total flow should be equal.
For
for-
every V the total flow coming into the vertex is the total flow going out.
Exactly. So for all vertex V, if I look at the total flow coming into V, right, this must be equal to the total flow going out of V. Now this is true for all V not equal to S or T. Okay. So of course S has only supply. So S kind of keeps on passing things as it goes, and T has only is a sink, right? It's like goes in and that's it. So for every vertex here in the middle, I should, whatever amount that comes in must go out. And this is important. Okay, now this is what we have. This is a flow condition. This is a network flow. And what is a max flow? What do we want to maximize?
So the total flow into the sink.
This is maximize total flow. Which is it? What is total flow into the sink? Total flow into the sink is the amount of things that are going into
If
T
you
from all. So it so happens that this is also equal to the total flow that goes out of the starting state. Right. So you maximize this statement. You maximize. So max flow basically means maximize good. So okay, now can you guys, how many of you remember, or maybe I should ask, yeah, how many of you remember what you had done in your discrete math course in your flow structure? Do you remember the algorithm that was done or the steps that was done? What was the statement?
Sir, we did the fourth Fulkerson algorithm and we proved the max flow min cut theorem.
You proved the max flow min cut theorem, right? Now, what is the max flow min cut theorem? Do you remember the proof?
Actually, the proof somehow came like in the termination step of fourth full cutscene, I think.
Yeah, I mean, okay. So
So
maybe I
can we
will.
take a
Hmm?
inductive approach? Like if we consider the sink
Right,
and if we remove that from the graph,
right,
whatever are remaining, I consider them as like leftover pipes. So
right.
if I can whatever, so I take the maximum that can be possible out of those four and choose the one which is possible, like with the sink attached, like something like that, like inductive approach.
The problem is that you can do something like that, but you have to be careful that, see, it is like you can have flow, which is like, how do I say it? So some of it can go through this, some of it can go through this, some of them can go through here and here, right?
Yes, yes.
So it's a mixture of everything that's happening, right? So you cannot say, okay, how much mass can I send it from here to here? Okay, how much mass I can send from here to here? Yeah, but that possibly doesn't indicate how much mass. So if I even know
So
the maximum mass I can send from S to
to
here,
four, yes, sir, that green one, first green one.
yeah, this to here, say I know that. I also know how much mass I can send from here to here.
The max, yes.
I also know how much mass I can send from, yeah, so they're from, so both of them. But from that, can I say how much mass will I send from here to here? Actually not.
Yeah.
Why not? First of all, some mass can go through here, some mass can go through here. Okay, you can say the one, we'll just add them up or something like that. But issue is that the flow from here to here, right, and the flow from here to here might use the same pipes.
Yeah, yes, sir. So it's not going to be very trivial like this.
It's not
So,
trivial. You cannot separate them very nicely.
okay, yes, yes, yes.
Okay. Now, of course, it's okay. So now if I ask you guys to solve this problem, okay, can you give me an algorithm, a polynomial time algorithm for network flows to find the max flow? Okay, so let's start with this thing. Okay, say that I just give you in the question paper suddenly this thing that, okay, here is this concept of network flows, here is the max flow definition. Given a graph, how can you compute or give me a polytime algorithm for solving max flow? How will you do it? Of course, you guys told that some of you have seen fourth full cutscene, right? Or remember fourth cutscene somewhat. Okay, I mean, you have not, I mean, actually fourth full cutscene is in fact polynomial time algorithm. But do you know how to solve, do you remember this algorithm properly?
Sir, we start flow from the sink, and whenever we exceed the capacity, we like somehow reverse. Like some
Correct.
type
So
of
we do something like that. Right, you're completely right. I will go over it once, okay? But yes, you're completely right. What I'm saying is that if I'm just wanting polynomial time algorithm, there is a very simple algorithm for this. Just look at these things. Look at this structure. Does it ring any bells to you guys? What is going on? So maybe I should write it.
Sir, is it an LP problem?
It is an LP problem. Exactly. So you have been given G and weights. And what do I want? I want to maximize summation of f su sum over u such that summation of, so first of all, as you guys wrote, 0 is less than f e w e for all e, and summation of f u v is equals to summation of f vu for all v not equal to s comma t. This is nothing but a set of linear constraints. What are the variables? What are the variables here?
The functions.
The functions, f's, right? Meaning f of uv for all uv basically, and f of e for all e in v. So these are the variables. So this is a linear constraint, and you are maximizing this. And note that f's are just reals, right? So this is nothing but a linear programming instance. So this is where you kind of see this beauty of it. The linear programming is such a powerful thing. If you have a good algorithm for linear programming, you just represent this flow problem as a linear program and done. Game over. Is it clear?
Yes, sir.
Yes, sir.
So we also know that linear program is in P, right?
Yes, sir.
So it has a polynomial time algorithm. It is not an ILP, it's a LP. Right? Good. Now, let me ask a slightly different question, okay? So this question you have done, I will come back to Fort Fulkerson very soon, okay? I will try to give you some ideas of how the Fort Fulkerson is working and what are the properties and why do you need Fort Fulkerson, actually speaking. Okay. Or maybe I should do it right here. Okay, let me do that here. Okay, first of all, let me write the theorem. Okay, you guys also know the theorem. What is the theorem that you know? That max flow equals to mean cut. Now this is something you have done. Okay, so this is you have done from your previous class, but I'm not asking you to prove it in some sense, but I'm just trying to understand what is this statement saying? What is this statement saying? What is a mean cut? Do you know what the mean cut is?
Sir, if we like partition the vertex set V into two sets S and T, such that sink is in S and
Yes.
And source is in S and the sink is in T.
Right.
So cart is defined as the total, the sum of the weights of all the edges going from S to T.
Yes.
And flow is like the total flow from S to T. And so we can prove that for any such partition S and T, the flow value is less than or equal to cart value. So from that, if we take the maximum in the
wonderful, excellent. So for a particular partition of the vertex set into two disjoint sets of U and V, such that S is in U, T is in W. W is a very bad option. I've used W twice. Maybe I should use something else. Okay, say S and T such that small s is in S, small t is in T, then the cut, okay, or what is called this cut ST. What is this? This is the sum of the weights of all the vertices, also all the edges, such that the U is in the set S, T is in the set T. Okay. Now, of course, mean cut is the minimum cut of ST for all possible S and T, right? Fine. I mean, all for S and T satisfying that S T equals to V. Good. So this is what is mean cut is. Now, as your friend just now told, that what's happening here. So look at this graph, say here. Okay. The question is that can this graph has flow more than, say, 11? Can this graph has a flow more than 11? Hello. So in this graph, is there a flow which is more than 11?
No, sir.
Why not?
Can't.
The sink
Because
is
The sink. So if you look at this one, there's only 11 amount of weight is entering the sink. Right. If only 11 amount enter the sink, then how can you push in more? Of course, that's not possible. Right. But can you do something else? Okay, now let's see. Can there be a flow of size 8? Can there be a flow of size 8? So the main idea is that if you draw a edge over here, okay, a partition, so there are some
because
edge,
4 plus 3 is 7.
yeah. So if you have partitioned them, right, such that the things on this side, of course, that is my capital S and this is my capital T. So any flow that moves from this side to this side, right, has to cross this path, has to cross this partition in some sense. And if it has to cross this partition, then, right, if the total mass that is going through it itself adds up to less than some quantity, it adds up to say T, not T, say R, then you don't expect more than R amount to flow from S to T. That's kind of very obvious, right? So here, for example, what was 3 years? But here, for example, here, this is a cut. Look at it. There are only, so I have these two vertices in one side, which contains T, and the rest of them is on other side. So the flow from S to T has to cross this wall, right? And the only total number of edges that goes on the other side of the wall, okay? So maybe I can add some more edges or vertices also. So let me, there is a vertex here, say, which is 10. Okay, going in this direction. But even then, the amount of weight or some of the weights of the edges that are crossing from the S side to the T side of this wall is bounded. Some of them is 7 plus 3 is 4 plus 3 is 7. So that means clearly from this graph, you cannot have more than 7 edge weights now flow, right? So this is one cut. Now, if you find any cut in that respect, any cut wherever it is, okay, and that cut is such that S is in one side, T is on the other side, then of course the amount of things that you can move from one side to the other side cannot be more than the cut value. So which means that, so clearly from here we get to see that max flow is less than equal to mean cut. Okay. Now it so happens that these two are actually equal. So this is something that you saw it in your course earlier. Okay. So I will Ford Fulkerson, this is what was kind of proved. Is that max flow is of course less than or equal to, but this is actually equal to mean cut. Okay. Now, you guys all understand this cut thing? Correct?
Yes, sir.
Yes.
Wonderful. Can you write the cut as an LP? Maybe I will give you a couple of minutes to write this cut issue as an LP. Okay. Yeah, and let me give you this. Write this cut into as an LP.
For finding the curve or
But
for finding the cut
minimum,
or
finding
using...
the minimum, no, finding the minimum cut. For finding the minimum cut.
Okay, sir.
Sir.
Yeah.
So we minimize over different subsets of, like we choose a subset of V.
To the subset of V. Okay, but is then what are the variables? Okay, let me tell me the variables. What are the variables indicating?
So I'm trying to minimize summation WUV only, that this thing, the cut that you've written, and I'll be iterating over all subsets S, and with the constraint that source belongs to S and T belongs to V.
Hold on. Think of this linear programming. Okay, in linear programming,
Okay.
you have a set of variables.
Yes, sir.
Okay, the constraints are linear constraints on those set of variables. Okay,
Yes, sir.
and you optimize a linear function of the variables.
Yes.
Because how it is written here, this is not.
No. Yes, sir. It is not.
Okay, so think about
Yes.
it and try to write accordingly. If not LP, and ILP is also good enough for me for now. Okay.
Sir, so in an ILP sense, we're trying to look at summation AI times the C values or sorry, W values, right? And where AI is either 0 or 1.
I mean,
this
what is AI?
AI is just a selection indicator. So whether an edge is selected in the minimum cut or not.
Okay, then why don't you write it? Okay, then see. I mean, how do you kind of ensure that that's a cut?
Right. So we need to impose some conditions on the AI.
Yes, that's what I'm asking. How do you write that? Yeah.
Okay. So, but then that will be an ILP, right? It can't be an LP.
Okay, write an ILP for now. It is an LP also, but okay, write an ILP for now.
Okay. So do we know that all the weights are positive?
Yeah.
Okay. So any selection of edges can pass as a subset of a cut of some cut if there are no cycles within them, right?
Sorry. Can you say repeat once?
Say any subset of a cut in any graph can be passed as any selection of edges can be passed as a subset of some cut in the graph if there are no cycles in that selection of edges, right?
No. That's not true. That's not true. Any subset cannot be a cut, or even a subset of a cut. Okay.
Oh, okay.
Yeah.
Sure, because if we can just ensure that whatever conditions we impose imposes the condition that this selection of edges will be a subset of some cut, then we're done, right? Because then the maximization process will make it a cut, right?
Sorry.
So if we can just impose the condition,
Yes, you can impose that condition. That's good. Yeah.
That if it has to be a subset of some cut, then it will be
Right.
a cut when we try to maximize.
What is a subset of a cut? So
if you're talking about cut as a selection of edges from S to T, then it's a subgraph, right? And then the subset of a cut is just a subgraph of that subgraph, is how I'm trying to convey that.
Yeah, I mean, think a bit. Okay, think a bit. You can do more. Just don't think only on variables on edges. You might want to think something else also. Okay, writing an LP, you might think a little bit more on this setting.
So something like you're saying that we can introduce the vertices as variables, and then whatever their coefficients are, they can be 0 if the vertex belongs in S.
Yeah, you can do something like that.
Okay.
Something like that. Yeah.
we need a fixed number of variables before doing an LP, right?
Not a fixed number, but yeah, a polynomial type number. Yes, polynomial and many variables. Actually, you can have more than polynomial variables also possible. Now, you have to kind of tell me the variables. How do you write this one as a linear program? This thing, am I minimizing something? And how?
Sir, so
Sir, we can write this like, sir, in LP the constants are linear, right? We can maximize the optimizable function that we are optimizing. That can be anything, right? Sir?
Yeah, can you repeat once? What is it?
So I'm asking that in an LP,
right,
the constants are linear, but what we are trying to optimize, that may not be linear, right?
No, that also has to be linear. Everything is linear in LP.
Okay.
So
yeah.
Sir, so on the same thought as before, let's say we want to optimize summation A u comma v w u comma v plus b.
Okay, can you just say what are this A and B thing that you're writing? I mean, can you intuitively what is it? What are you trying to think of?
Right. So A u comma v is 1 if the edge between u and v, which are vertices, that is a part of your cut, right?
Okay, fine.
And otherwise 0. And b, and so summation A u comma v w
you
comma
want
v,
the summation u comma v, you want to times w u comma v, you want to minimize this.
So summation A u comma v.
Summation A u comma v, right?
And right.
How do you say that the cut?
Maybe every path that forms is disconnected. If I
good, very good.
So maybe for a graph, there may be polynomial number of paths. Like there are polynomial number of edges with respect to v, the vertices. There are polynomial number of paths, maybe. And then if I pick a edge so that it is a cut, like at most one from each.
So what you're saying is that for all, we want to ensure that every edge. So if it's a cut, that means every path from from S to T has been cut, has been broken. So summation of AE, basically all the edges, E is in some path. This must be more than or equal to 1. Right? P is the set of paths from S to T. And AEs are 0 or 1. Right. So this is in fact a good concept of it's a linear program. Let's put it this way. Why? So I am minimizing this cut. I am AUV is kind of considering whether which edge will go, which edge I am taking, right? And it is a cut in the sense that all paths have at least one edge removed in some sense. Right? All
so,
paths.
The number of paths from
right.
S to T can be more than polynomial, right?
Right, exactly. So as what I think Abhijit told, number of paths from S to T is not polynomial. Abhijit, are you fine?
Yes, like, because edge is at most polynomial number of edges.
So
path is like.
So are you saying that it is polynomial or not polynomial?
Yes, yes, polynomial.
No,
I
it's not.
Okay.
Number of paths, or basically, in other words, the size of this P is not polynomial, not. But this is where things are very interesting, by the way, I must say. Okay. Although this is a linear program, no doubt, but not a polynomial sized linear program. Okay.
Sir, so in a linear program, we say that it is polytime, but then it is polytime with respect to the number of bounds or the number of constraints as well.
No, so that's the thing. We take polytime in respect to the number of variables. Okay. And actually speaking, surprisingly, even this kind of polynomial LPs, where there are exponential number of different constraints, but polynomial number of variables, they can also be solved in polynomial time. Polynomial in the number of variables.
But the matrix, like it is becoming exponential, right? Because there are exponential number of constraints and all.
Right. It is exponential. I completely agree. It becomes exponential. But still, you can actually still, I don't want to go into this too much. It can be solved in polytime.
Sure, so there probably are many redundancies, right? In those.
That is one thing, and yeah, I don't really want to go into this too much into this whole thing. Okay, but you will get to know more of this thing as when you do optimization course in your MStat program. Okay. Yeah. So optimization. So in some sense, this is the start of your optimization course that will happen. Okay. How do you solve an LP? What kind of stuff that you can solve? When can you solve it? Okay. Let me just tell you another thing. Okay. So, okay, what happens if you do this stuff? Okay, good. So you have this is the max flow and this is the min cut. Okay. Now, so it is. How do I go about it? Just 1 second. Yeah. Okay, good. So where are we now? So let me just recall where we are. So we had this max flow, this problem. This is an LP. We found that the min cut is an ILP, right? But surprisingly, I also have this theorem that max flow equals to min cut. So while min cut, so min cut is an ILP. I mean, even forget this fact that it's an exponential size or not. But the issue is that it's an ILP that is much more complicated than an LP. Right? Whereas this problem, this max flow is an LP. So that means you can solve max flow in polynomial time. Min cut as such cannot be solved in polynomial time immediately. It's not clear how can you solve it in polynomial time. But we have a max flow min cut theorem. Right? So using this max flow min cut theorem, what can we say?
So that the subset of inputs in this ILP are such that it is polynomially solvable.
Right. Max flow is in polynomial time solvable, and so is min cut. Both of them are polynomial time solvable. Okay, so good. Let me go for a slightly different question, okay, on the similar flavor. By the way, I can hear only 2 or 3 people are answering. So I'm hoping the people who have joined here, you guys are trying something as I'm telling you guys. If you are not, then that will not be very helpful to you guys. So I have this something called a matching. What is the matching? So you have been given a graph, right? And a matching is a subset of this edge set such that for all u in V, okay, there exists at most one vertex V such that UV is in the edge set. So I want to kind of pick. So if I have a graph like this, and this is not directed necessarily, okay? I want to pick some set of edges over here, here, like this, such that these are of what is it called? So these are like these are matching, right? Now,
So it's like a dual
Yeah.
concept of an independent set, right?
it is the independent set is on the vertices.
Right, right.
So this is on the edges. Right.
Yes, but it's something similar.
Yeah,
right?
something similar. You can think of it that way. Yeah. So these are the edges that don't they don't have any intersection.
Right.
So in some sense, why is it called matching? Right? It's you can understand that. Say you have a you all of you come to ISI, and you guys have preferences, right? So there we have hostels rooms, and in hostel rooms, every room has to be shared by 2 people. Right? Everybody gives their preference. That, okay, I am ready to share with this person, or this person. Somebody else says, oh, I want to share with this person, or this person, and so on and so forth. Now, at the end of the day, the institute is supposed to honor your preferences and assign each of you a room, right? And such that if 2 of you are assigned, I mean, if you are assigned another room and you are sharing that room with somebody else, then there is no 3rd person in the room, right? So in some sense, you are matched with your roommate. So it is exactly that. So if you draw a graph of the preferences of roommates, then the matching gives you a set of roommates. Right? Now there can also be other matching. For example, here there was this matching. Sorry. Now I could have used this matching, maybe this matching, and then I would have got this matching. So I have a 3 matching, a matching of size 3. Right? So one would like to have a matching. Okay. I want to solve this matching problem. I want to, given a graph, I want to find the maximum matching. How will you do it? So let's, as I just now told you, as we the kind of flow of this thing, can you write this problem of finding the maximum matching as an LP or as an ILP? Please try to write this problem of maximum matching as an ILP or an LP.
Sir,
Yeah.
sir,
Yeah.
again, with the same thought as before, now the constraints can be related to every single vertex, right? So the constraint for any vertex V would be that the summation of A, V, comma, W for W belonging to the whole neighborhood of V.
Think. Write it out, okay? So let's give people, let's give you and the people couple of minutes, think and write down what is it. This is easy actually, believe me. Much easier than the mean cut.
Okay. So but why won't this work where we're looking at just here we don't need to okay, we do, right? So we want to optimize summation
These are
of
variables. Variables are for every vertex.
so the variables are again the edges.
Okay. Okay, you are right.
Summation.
I think you are in the right direction, or you are having the right. Yeah. Let somebody else answer also.
Okay.
So what about rest of you? Did you guys manage to get something to write to manage to write the LP for this?
So yeah, I got it. So it's like so I have to pick up maximum number of edges such that like standing from a vertex, I pick up at most one edge.
Can you write it in a linear program
Yes,
as a
yes,
linear
yes.
constant?
Yes, max summation of xe, where for all xe is I pick up the edge e. One if I pick up the edge e.
Okay.
To
You are saying the
maximize
max sum
sum.
of xc. So xc is basically a variable that is supposed to indicate 1 if e is in the matching M and 0 otherwise.
Yes, yes.
And I want to maximize the number of vertex edges picked up such that now I have to ensure that it's a matching. How can you ensure that it's a matching? That for all vertex u, look at the set of x uv, right? All of them that are going out of u or adjacent to you, this sum must be less than or equal to 1. It cannot have more than 1 edge in that. Now, of course, the problem is that x's are either 0 or 1. Is this thing clear?
Yes.
Yeah. Everybody is clear. I can see a lot of people today.
Yes, sir. It is clear.
Okay, good. So, okay, so this is a matching. Now, problem is that, so we have written this matching problem as an LP, and an ILP. But that does not give me a full-time solution. This does not give me a polytime algorithm. Right? So how can you go about this polytime algorithm? Good. So I think this is the time to go back to this problem of flow, network flow. Okay, so let's see once again, this network flow problem. Okay. So I have a S, I have a T, and so I know the network flow can be solved in polynomial time because it is in LP, right? I can formulate it as an LP problem. But let's try to do it in some other way. Instead of going through the LP, let's see if I can come up with a different algorithm, something that you have seen already. And I think some of your friends have already kind of pointed out, right? So the main idea is that you apply kind of like a just one second, let me just quickly see what is going on here. Yeah. Actually, I have to come up with something else.
Sir,
Sorry. Yeah.
sir, when we are reducing any problem to another problem, essentially we're trying to learn a function from the language, which is a subset of the input to the other language, right?
Right.
So here we've shown that there is a certain subclass of ILP on which we can map the language of P.
Correct. On we can map the language of P by map of network flow.
Right. So a subset of some language in LP, we can map to a subset of ILP. And then if we can show that that subset of ILP can be mapped into the subset of ILP, which is the matching problem, then we would show that it's a polynomial time algorithm.
Right, we can do that, right? So, okay, so this way I'm going to do it is that sometimes, okay, when you are trying to, so we do represent this thing as an ILP, right?
Yes, sir.
Right? Now, it has some other structures in it, right? It is not a general ILP. It has some structures in that ILP.
Right. It's a subset of the inputs is a subset of the.
Yes, the input has some structures. Let's put it this way, right? Certain kind of a. It's not a very general setting, right? It's not a general ILP setting, right? So for this spatial ILP setting, or for problems with this spatial structure, can you solve it?
Right.
Okay. Now that is exactly what we are trying to prove, and we'll actually end up giving you a polytime algorithm for this problem, for the matching problem. Okay. Now I will give it in 2 steps. In the first step, I will give you a polytime algorithm through network flows. Okay, and this is what I will do today. And in next class, we will give a completely independent polytime algorithm. Okay, but to get that, I cannot rely on just LP to solve network flows. I have to go back to the problem that you have seen in some sense was basically the Ford-Fulkerson algorithm. So what is a Ford-Fulkerson algorithm doing? Fourth focus algorithm basically is a very greedy algorithm. What it does is that it just says that, okay, here is something, here is a graph. I find a path that connects, say, S to T. Okay, that's all I do. I find a path. Okay, find a path from S to T. Okay, and pass as much flow you can through the path. Now this makes sense, okay? So say for example, I will write this way. So I kind of find this path, say here. Okay, now there's a path, and I say, okay, I have to pass as much flow. How can I send as much flow more? I mean, what is the flow that I can send through this path?
So the bottleneck edge with the
The
minimum.
bottleneck edge will be the thing, right? So in this case, the bottleneck edge is 3. So I can say, okay, that means I will send 3 units from here, 3 units from here, 3 units from here, and 3 units from here. Okay. So the red color kind of says that this is the flow. Okay. Excellent. Good. But now, once we have done it, right? Let me kind of let me erase a little bit. Okay, that will help us to kind of quickly understand what's going on. So sorry. Let's think of this one. Yeah.
So we also discussed the residual
Yeah.
graph.
Exactly. So now what happens? Let's try to see what is the residual graph of this. What does the residual graph means? Okay, I will try to copy it. I will use all my gadget trick to kind of explain this whole thing. Okay. Very good. So let's see. At this point, how much is left over? Right? What is left over is that here I have already used 3 units, so I am left with 0. I have used 3 units, I am left with 0. Here I have used 3 units, I am left with 0. Here I have 3 units, I am left with 5, and here I have 3 units, I am left with 7. Great. So in some sense, if you can think of it, that this edge has kind of vanished, this edge has vanished, this edge has vanished. But is that so? In some sense, now the residual graph would be like this kind of stuff. Sorry. Residual graph would be something like this case has vanished, this has vanished, this has vanished, and this has gone down to 7, and this has gone down to 5. Right, and of course there is this red edges that are there that keeps on coming up. So I was 3 edge going here, 3 edge going here, and 3 edge going here. So 3 edges are not part of the graph any longer in some sense, right? But do you think that can I push in some more flow through this graph? So I've greedily found a path, pushed in as much things as I can. Now the graph has become disconnected. What can I do now? So the thing is that one would naturally say that, okay, why not try to push some, sorry, I have a bad job. Why not try to push something through here? Okay, but problem is that this has become 0. Okay, not good. What happens if I push something through here? What do you think is possible problem? Why can't I push something through here?
So these are disconnected components. So
They're disconnected. But think of it. What's going on? If I come up with a 3, if I say that, okay, I want to push 3 unit of mass through here. I send 3 unit here, the 3 unit goes here, 3 unit comes here. Okay, so I'm right now here at 3 units. Then I try to push 3 unit here. At this time, what is happening? 3 unit is coming in this direction. And I'm going to force 3 unit back. Is that possible? Why not? Let's see what happens. If I decide to pass 3 unit here, okay, or 2 units, say, I put 2 unit here, I send 2 unit here. I'm just saying this is, I'm trying, I want to push 2 units back, and then I will end up using this one to send 2 unit and this one to send another 2 unit. What will happen? What is the effective thing that can happen? Let's see. This edge is fine. Okay, this edge has 2 units, this edge has 2 units, this edge has 2 units. The issue is in this edge, right? What is happening here? You are giving me 3 units. I am giving you back 2 units. So effectively, how much units is coming here on this path?
1 unit down.
It's 1 unit down. Was 1 unit an allowed quantity here?
Yes, sir.
It was. So in some sense, I can go against the flow. The idea is exactly something that I guess you guys all do it regularly. Okay, say you have something like this game, say something like that. A has to pay B 5 rupees. B has to pay C 5 rupees, right? And so D has to pay just one second. Let me try to see. Yeah, so forget C. See? And the C has to pay 5 rupees to A. How will you solve this whole problem? Do you guys solve this thing? You basically say that everybody has to pay everybody 5 rupees, right?
Yes,
So in
sir.
that case, you don't pay anybody anything. What is basically happening here? Why is it that the solution? Because when B kind of says, okay, here is your 5 rupees. Good. At that point, sorry, I should write color things. Okay. B first pays 5 rupees to C. But C then says that C, okay, forget this 5 rupees. Okay, you don't give it to me. You keep it with you. Instead, I am actually have to give A 5 rupees. Then why don't I push 5 rupees to A through you? Which is basically saying that, okay, see, B, I give you back 5 rupees. You instead go and give it to A. Right? So that effectively that basically becomes that, okay, so I am done with my job. I am no longer, I have paid my stuff, so I don't have to pay. You have to not pay. You don't pay me anything. Now B has to pay 5 rupees to A. So I've gone against the flow. You guys do it all the time, right? I assume. If you have to pay somebody, somebody has to pay, you can try to redirect this whole thing. This is exactly what is happening for here. So when there is a flow going from 3 unit from top to bottom, it is as if I have the ability to push back up to 3 units in the other direction. I am allowed to do that. That's a valid thing. Okay. So what I kind of wrote here, that this is an effective graph, this is not true. This is not an effective graph, not the correct graph, not the residue graph. Because it is true what I have written here. Okay, it is true what I have written here, that the capacity on this edge has gone down to 0. This capacity on this edge has gone down to 0. This capacity on this edge has gone down to 5. Perfectly fine. But what I have not told is that on this edge, I now can push 3 units back. So this red 3 units coming from top to bottom is causing a reverse path of 3 units from bottom to top. Similarly here, similarly here, similarly here, and similarly here. So it basically says that, see, you could have gone, say here, say in this case, you could have sent, maybe I will add an U or something. You could have sent up to 5 units from U to T. At this point, you are sending 3 units. So what is left? So you can say that you are left with, or you can send 8 units, right, to start with, from U to T. You are sending 3 units. So at this point, you have 5 units that you can send more from U to T. Also, since you are getting 3 units from U to T, it is almost like you can refuse to take the 3 units, which in other sense saying that I can send 3 units back from T to U. So this reflective graph, therefore, okay, is this new graph, GF it's called. Okay, so this is basically, so GF is the residue graph. Residue graph. Now, what is the residue graph? Let's kind of, I can define it formally. Okay, so I have this graph, right? And I have been given this flow. Okay, first of all, you realize that f of E, right, is less than W of E, that we know that. So this is something that has been given to me. Now, what is the residue graph? So residue graph is basically, in this residue graph, the weight. So edges are kind of, we will come to that edges first. Okay, so for all UV, okay, the weight of UV is how much? The weight of UV is the amount of flow left over, right? So it is like, so maybe this is WF of, so W of UV, amount of flow weight that was there, minus the flow that was going from U to V. And this is if FUV is strictly more than 0. Okay, fine. Okay, maybe. So maybe I should write this opposite way. This is if F of VU is equals to 0. So if I have nothing is going in the other direction, then this is the case. Now what happens if it is the other way? Now if V of U is not equal to 0, which is basically more than 0, then what is this weight? This is like, okay, in the opposite direction, I have a flow. In that case, this one is actually equals to F of VU. So this is the effective graph, the thing that's coming, effective graph. So is this residue graph fine? Is it clear?
Yes, sir.
Yes, sir.
Okay, excellent. And what is the main idea, the lemma you can think of? Okay. The lemma is that if G has min cut R and F is a flow of size Z, then GF has a min cut of size R minus Z. So of course, if the graph is initially disconnected, there's no chance of it. Okay. But so as long as your flow size is not reaching the min cut, you will have a min cut non-zero. You keep on having. And another lemma that I'm going to write here, and I'm not going to prove either of them, I'm leaving you guys to prove it, is that if I take a path, if P is a path from S to T in GF, okay, and consider a flow of size consider flow, a valid flow, let's put it this way, a valid flow from S to T via the path P, then F plus P is a valid flow in G. So if I have a flow, I look at the residue graph. In the residue graph, I still find a path, then I can push that much amount of mass or flow from S to T, and the resulting flow will be the kind of combination of these two, and that will also be a valid flow in this G. Now, both of them are very obvious statements if you just think of it a little bit. And since you have told you have done float fluid cursor, I'm not going to do it in full details here. But basically, this gives us the Ford Fulkerson algorithm, which is exactly how you would kind of okay. So basically, while GF, okay, so when you start with the GF equals to G, while GF has a path from S to T, what do? Push push a valid flow, say F tilde from S to T in GF, okay, any valid flow, and update GF basically gets updated to G of F of this F tilde. So once you have pushed this one, then what happens? Which is basically nothing but G of F plus F tilde. And keep on doing it. And that is. So basically you find a path, you try to push as much as you can through that path, create this GF. Then you find another path, okay, and you try to push through that, and you continue like that. Is this clear?
Yes, sir.
Yes.
Sure. Okay, so because I'm going to ask you certain questions now.
Sir,
Yeah,
sir, could you scroll up to the min cut statement?
min cut statement.
Sir, no, sir, the min cut lemma. The first one of the two lemmas that you.
Yes, here.
So a flow of size z meaning.
So if I give you a flow, what's the size of the flow?
Okay, so like 3 was the size of the flow. In the...
Yes, size of the flow is always the amount of mass or amount of flow going out of S.
Okay. So the flow that we choose is always maximal in that sense, using a bottleneck edge in whatever
You can
path
think
we-
of it. Yes. Okay.
Okay. So why is this statement true?
Why is which statement true? The first statement?
Yes, sir.
Yeah, why is this statement true? Okay. Let's see. Okay, so let's consider the kind of the extreme case. Okay, that will be slightly easier to kind of view. Is it possible? So I have say a graph here. G, I have an S, I have a T, and say I have the mean cut is equals to R. Okay, and I have a flow. Okay, I mean the flow can be of a various kind, right? I mean, and then of course there are this edges are also there, which are the standard edges, right? And there can be edges otherwise. Is it possible that I have this flow, size of the flow is less than R, and GF is disconnected, is not connected? Is it possible? Let's say, or it's not ST connected? So I'm basically have a flow of size less than R, strictly less than R. And is it possible that I have managed to use all the possible paths from S to T? Let's see. How can it happen? Okay. So say it happens. So what does it mean? That in the GF, now if I draw this GF, okay, let me erase some of these edges and you have kind of rely on your. So there is this set of vertices that are connected to S. Okay, these are the connected vertices to S, and these are the vertices through to which there is a path from S, right? Let's call this one S. Now this is the fact. So if I'm proving it by contradiction, that means I have managed to have this flow. So GF has managed to disconnect S and T. So I mean T is outside. Okay, good. Now consider all the edges that were there that went out of this set. Okay. Okay, this is originally that was there. Consider all the edges. So basically, if I want to write it, okay. So let by contradiction, let GF be disconnected. Be disconnected. So then consider S the set of all vertices that are reachable from S in GF. Okay. So since GF is disconnected, what can we say? That T is not in the set S. Correct. Good. Now consider since G of S is disconnected implies T is not in set. Now consider the set of all edges UV where U is in the set S and V is not. Okay. What can you say about this set of edges? So these are the edges that are from here and going out.
So the sum of them is greater than R.
Of course, the sum of them are greater than R, right? Very good. But something else.
The flow is the value.
How? Yeah. Why?
Because this is exactly, I mean, the flow from S to T will pass through this.
So what is the flow from UV? What can you say compared to its edge weights? What do you think?
Less than. F is less than W.
If it's less than W, is it less than W? Think. If it is less than W, say I have this edge here, right? Here the weight was 8 and I am passing 7 through here. Then in the leftover graph, in the residue graph, which is G of F, what is happening? I have an edge going out of size 1, right?
Yes, sir.
So how can this be the vertex that is going out?
Right. It has to be equal.
Right? So it has to be equal. So the flow has to be equal. Now I know what. Okay. By the way, this is a comment. Okay, I should write it. So this is the case, but we still cannot say. But still, we cannot say that summation of FUV is greater than or equal to R. Why? Let's call this one E prime. We cannot say.
The min cut was R, right?
Good. Yeah. What
And
min cut was? What is min cut? Let's try to understand. What is this? What is the cut S complement? What is this? This is summation of the WUV, right? U is in S, V is in S complement.
Okay. So here,
but what is the flow? Yes. What is the flow?
It is summation of WU comma V. U is in S and V is in the neighborhood of S.
That is true. That's fine. Okay, there are all the edges minus all the flows that are coming back into it.
Oh, okay.
See, so cut doesn't have it. So in some sense, what I mean to say is that if I have a graph like this, and I have a graph, say the edge weights are, so edge weights are say 3, 2, 1, 1. 1 or say 2, right? So look at this cut. What is the size of the cut? size of the cut is how much?
2,
Is 2. But what is the size of the flow?
0.
No, not 0.
I mean,
Size of the okay, I have not even told the flow. That's the main problem. So what is the flow? I want to redirect some amount of flow. What is the flow? Flow would be 1 here, 1 here, 1 here, 1 here, and 1 here, right? So what is the flow?
Flow is 1.
it's 1.
Flow is 1. So although in these two edges they are tight. Okay, good. So that's the problem here. So flow is there, size is here. Now, but we are not yet done. Okay, so in those edges, this is the case. Okay, we cannot still finish this whole thing. Now let's look at it. What happens if I look at the other set? Say E double prime. These are all the set of all U or VU, where V is in S complement and U is in S. What can we say about them?
Equals minus of W. No, equals 0.
Yeah, why is it equal to 0?
Because if they were anything positive, then there will be an edge from S to S
Exactly.
complement in the residue.
Yes, if it was non-zero, then in the G of F, there would have been a edge in the opposite direction. Right? I mean, that's how the G of F is told. Like G of F is basically saying that, okay, at this point, so let me try to draw it here. Okay, so you have a flow that is coming from here to here. Maybe that flow comes from some various other sources. Okay, but in this flow, this thing flow is say 3 flow m unit is flow this way. It means that I can push this flow back 3 units. So that means in G of F there is this green edge that is there, right? Which will contradict the fact that I kind of assumed that this is the maximum set of, I mean, S was just did not contain this vertex, right? So I can say therefore this is equals to 0. Is this clear?
Yes, sir.
Yes.
So now we can say by this definition, okay, that this cut must be equal to the flow, right? Which would contradict the fact that the flow is less than R. Okay, so in some sense, after this, we can now say, so we can say now that this is exactly equals to, so sum of this set minus the sum of this set is R, this is 0, so it is R. Okay, so this we just kind of told that if you are passing in less than R flow, then you are left with something. Okay.
Yes, sir.
Okay. So I think I kind of gave you the whole proof of it to some level now. But okay. Coming back to this whole thing, fourth full cursor. There are certain things to notice about fourth full cursor. And I want you guys to think about one of them at least. I will come back in the next class and talk about it. First of all, what is the time complexity? See, I mean, if you go back to this Ford Fulkerson algorithm that I wrote here, how you go about it? You consider this residue graph, you find a path from S to T, try to push as much flow as you can from S to T throughout that through the path, and update the flow and consider the residue graph. Right? Now all these steps can be done in polytime, no problem. Right? Finding a path from S to T can be done in polytime. Finding the minimum edge weight in that full path can be done in polytime. Updating this graph can be done in polytime. Okay. In fact, they can be done in linear time, all of them. By the way, just quickly ask someone here, maybe someone who I have not seen here too often. That Mrilan Saini, are you there? Mrinal Shiny? Okay, doesn't seem so. Ritam there? Ritam there?
Yes, sir.
Yeah. Can you tell me how can we find a path from S to T? In linear time? Wonderful. Rajit Goel. Rajit Goel.
Yes, sir, I'm there.
Yeah. How can we find a path from S to T in H of G of F in linear time? Not a very good situation. Lokesh Siva.
Yes, sir.
Yeah. How can we find a path from S to T in G of F in linear time? Lokesh, I had a chat with you the other day and you told that you were watching my video. You still want to say that?
No.
Okay. If this is the situation after watching my videos, then I feel pity for myself. Zaida?
Yes, sir.
Yeah. Can you say how can you find a path from S to T in G of F?
Sir, DFS or
DFS, BFS, anything will do, right? You just do a traversal from S and see whether you're reaching T or not. And that's it. Good, very good. So, I mean, very good to the person who answered and very bad to the person who did not answer. So anyway, so with polytime, you can run one shot. But what is not clear to us is that how many times does this for while loop run? We don't have a, yeah.
At most, actually the maximum weight, because we cannot send more flow through that path, right? So
good. So you kind of assumed something already and you have told something correct. Okay. But let me put it here. The second point is that first of all, okay, and this is where the things are interesting. Okay, you kind of, why the maximum weight? You told, right? So
it's not minimum weight will do, because yeah, it's any weight, because
minimum weight? No. Minimum weight what? Minimum weight of what?
Of any edge in that vertex.
Minimum weight of any edge in the path. that much flow I will send, right? But then repeat it, and so on.
So we know that with every single iteration, the
yes, this every single iteration, the
the
cut will
minimum
go
cut
down,
is
going down,
and by
right?
at least by the minimum weight.
This is where things are interesting. Think of it once. Minimum weight of what?
Of the whole graph.
If after the first iteration, it goes down by at least the minimum weight, right?
Oh, but then it may not, because we are introducing the reverse edges.
No, not the reverse edges. The leftover weights, they might be different, right? For example, here I use this edge for text only, this thing. Say this weight was 1.1. So the minimum edge weight was 1.
Yes, sir.
Right? But after I pass this one weight, how much is the leftover weight here?
Oh, 0.1, right.
0.1. So there is an issue here.
Yes.
The minimum weight of this graph need not remain as the minimum weight graph.
So maybe we have to take the HCF of all the weights. But this is just too much of a stretch.
HCF of A, when they are real numbers? What is the real numbers HCF?
Right. Yes.
Okay, so I given you this fourth full cursor algorithm. I managed to give you an algorithm, but actually it is not even clear whether the algorithm will stop.
And
right?
so we can't even constrain it with the number of paths from S to T, right? Because
we can't, because this kind of
we can consider the same path multiple times.
Yeah.
Right.
Because
something
the
like a
edges,
sorry.
yes, the edge weights are really going to be messed up even after some time. I mean, we might really be looking at some very small edge weights and keep on working on that.
So if age weights are arbitrary real numbers, then it may not stop at all, right? I mean,
at least for now, that's what it seems, right? I mean, at least it doesn't show that immediately how it will go down. So I want you guys to think what happens in that case. Will it go down? Can you give an upper bound on the amount of time that you take?
okay, but if weights are integers, then it will stop.
If the weights are integers, then what happens? So if weights are integers, then every time I update it or I kind of increase the flow by an integer value.
Yes.
Right? So the flow, if I can go a little bit further, the flow on each edge is an all. Okay, so this is very interesting. So this means if it is integer, then not only every time you are going down by once every time, I mean, and the minimum cut is going down by at least one, we are also producing a flow of integer values. Okay. This is not something that you can say with an LP. For example, if I have S, I have a 1, 1, 1, 1. What is the flow here? Total flow here is 1, right? I can, of course, how will you give me a total flow here? Okay, send 1 unit through here. This is 1, right? It's a flow. But you can also send 1, half, 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 and 1. This is also a flow, which is also value 1. So when you put this graph through an LP solver, you are not guaranteed to get a integer solution. But Ford Fulkerson will find an integer solution. Okay, so here we are in a very interesting situation that we now have a flow algorithm. It is in LP, so in some sense it can be solved in polynomial time. But if I give you the extra guarantee that it is all the integers are all the constraints are integers, then Ford Fulkerson will actually solve it in polynomial time, or give a very quick algorithm, polytime algorithm, to solve it such that the output is an integral solution. Okay, so let me say where we are now. So network flow is LP, which means that this is in polytime. But for integer network flow, integral network flow, of course, this can also be solved, but LP will need not give you a integral solution. Okay, Ford Fulkerson gives a integral flow. Okay, now I think I'll stop here today, but what I'm going to ask you guys is that use this observation, okay, to solve your matching problem. Can you now obtain a polytime algorithm for solving or for finding the maximum matching in a graph? Okay, by the way, I think I am really running out of time. I have a meeting at 4 also, and I just now realized that I also promised that I will answer the other question that you guys that I posed in last class, right, in the last tutorial. So why don't I do that one also next class only? Just please remember and remind me of that. And for now, so what we have seen today is network flows, and what happens for a special case of network flows when the constraints are integers. Okay, and we are interested in an integer solution, then Ford Fulkerson algorithm will give you an integer solution. Now, using this Ford Fulkerson algorithm, can you solve the matching problem, finding the matching problem in polynomial time? Is this fine?
Yes.
sir.
Okay, good. So let me leave with that, and we'll meet on Thursday. Okay.
Thank you, sir.
Thank you.